So I think we still have a few people trickling in, but I'll start briefly with the introductions. Uh, to us, my name is Pedro Sampaio, and I am part of the Taste of Science Houston team. Our mission at Taste of Science and Taste of Science Houston, our local Houston chapter, is really to bring science to the people and make science accessible to everyone, and you know, give people the opportunity to meet their friendly neighborhood scientists over a beer or two. We usually organize events in places where people like to hang out, like their local bars, restaurants, breweries, cafes. But obviously, right now, while we're in the middle of the COVID-19 pandemic, we're bringing science straight into your living rooms by organizing virtual events, which we are doing on a regular basis and will continue to do so over the coming months. And we actually have two Taste of Science events happening today, our own event, which we'll get into very briefly. But we also have later on today our first ever Spanish language event. And I'd like to bring in Jenny Masi from our team to tell everyone a little bit more about that before we get started.
Good afternoon, everybody. As Pedro just mentioned, today we're going to have, or the Taste of Science National Organization is doing a Spanish language event related to COVID-19 at 6 p.m. Eastern Time and 5 p.m. Central Time. The event is called 2020, 1 year to pandemics. They will be explaining the science behind the vaccines and correcting some of the misinformation that there is out there. If you're interested in joining this event, please check out our website, www.tasteofscience.org. And if you can make it today, we will have the video posted on YouTube shortly after the event is done. So now I'm going to basically say this information in Spanish for all our Spanish speakers. Buenas tardes, muchas gracias por estar esta tarde con nosotros en este evento sobre el clima. Y quiero informarles que la Organización Nacional de Taste of Science, en conjunto con nuestra organización asociada en Uruguay llamada Gusto a Ciencia, los invitan a un evento sobre la pandemia COVID-19 llamado 2020, un año, dos pandemias. Ellos van a estar explicando cuál es la ciencia detrás de las vacunas, cómo se generaron, y también van a corregir o van a clarificar algunos mitos que están relacionados a las vacunas. Si están interesados en participar en este evento, por favor, vayan y revisen la página web www.tasteofscience.org. Y si no pueden unirnos esta tarde, por favor, vayan a YouTube, donde el video va a estar puesto unos minutos después de que finalice el evento. Muchas gracias.
Gracias. Thank you very much, Jenny. And with that, I think we will go ahead and get started with our event today. So it's obviously been a very difficult year for everyone with the pandemic. But while we were experiencing the pandemic of COVID-19, we've also continued to be exposed to extreme weather events throughout the previous year. Climate change has been deemed by the United Nations and many other people as the defining issue of our time. But how exactly climate change is related to all of these extreme weather events that we have been experienced is really something that we want to delve into today. I think, like most of the other people here today, was living in Houston in 2017 when we were hit by Hurricane Harvey and witnessed the devastating consequences that it had in the local communities. And ever since Harvey, we've been continuously witnessing extreme weather events like that, such as Hurricane Irma, Maria, which had such devastating consequences in Puerto Rico, Hurricane Michael, Dorian, Delta last year in Louisiana, which really capped what I think was a record-breaking season of Atlantic hurricanes with more than 30 storms. I think one of them, actually Alpha, was the first ever subtropical hurricane to hit Portugal, which is where I am right now. And on a personal note, Portugal has also been hit by wildfires on an increasing amount over the last few years. So really, what the question is that we're asking here today is how these increasing extreme weather events are related with global warming and how climate change affects the weather patterns that we see every day. Now, before we get started, I feel obliged to clarify that this is absolutely not a political event, even though regrettably Facebook blocked us from advertising this event on political grounds. We are not here to talk about science. Our name is, as we said in the beginning, Taste of Science Houston. We're a science outreach organization, and we're here to talk about the science. And for that, we have a really, really great panel of Houston-based scientists that cover different aspects of climate science, and we'll be going over these issues with them. Now, the way that this event is going to go is I will introduce each of our speakers individually, and we'll be going sort of from the broad worldwide climate models to more focused sort of what's happening in our city at a physical level. And after all of our speakers have had the opportunity to talk a little bit about their work, then we will move on to the Q&A session. And people have had the opportunity to contribute questions previously through our Google Docs. So we do have a few questions that we want to go into, but I really, really want to encourage everyone while our speakers are talking, if you want to pop in your questions into the Q&A section in the bottom of your Zoom window, please, make sure that you keep contributing with them, and we will make sure that we ask those questions to the speakers towards the end of our event. This will be a roundtable informal event, very much like our vaccine event that we had in December, if people were there. So we want to make this a discussion and make it an interesting one. So on that note, I think I will go ahead and introduce our first speaker, Sylvia Dee, who's an assistant professor at Rice at the Department of Earth, Environmental and Planetary Sciences, and who focuses on combining historical and current data with the latest modeling techniques to predict future climate. Sylvia will be our first speaker, and we'll discuss how climate modeling and projections work in broad sense. So Sylvia, the stage is yours.
Thank you so much. Thanks for the introduction to speak today. And I was asked to give you a brief overview of how climate models work and how we use them. And Earth is an incredibly rare planet to study. We're the only planet in our solar system with life. And one of the things that's tough about Earth science compared to our neighbors in biology, chemistry, and physics is that we don't have an experimental planet that we can put in a test tube and perform experiments on. And really, we're performing an active experiment on the planet right now. And the climate system is incredibly complex. We have interactions between the atmosphere and vegetation and the ocean. And so in lieu of an extra Earth to perform experiments on, we use climate models, which give us a physical basis for predicting Earth's climate as we increase greenhouse gas forcing on the atmosphere. So what is a climate model? Very simply, we can dice the atmosphere and the oceans into tiny little boxes, as demonstrated in this little figure, maybe 100 kilometers by 100 kilometers. We give the climate model a starting point, and then we use conservation of mass, energy, and momentum to compute what happens moving from the starting time into the future. So for those of you who might be physics nerds, right, we basically solve 6 equations in a climate model. We have the change in the winds with time, or conservation of momentum. We have how temperature is changing with time, or conservation of heat. So here's our T for temperature. And then finally, we conserve mass, or here rho, or density. So it might seem daunting, and it really is about 200,000 lines of code or more, but really we're just solving a few equations in every point in space and time. So if I were to open the climate model that I use, for example, which is called SPEEDY, affectionately, because it runs very fast, there are lots of variables in here that you probably recognize: wind, temperature, humidity, wind stress, sensible heat flux. These are all sort of variables that in climate and weather science we all use all the time. So climate models have improved and changed dramatically since we developed computers. In the mid-1970s, we had very simplistic models that maybe only had a single grid cell. We could force them with carbon dioxide. Maybe they had a basic hydrological cycle. And moving forward in time, our climate models now have advanced atmospheric chemistry. They have interactive vegetation. They have clouds. We've come a long way in the physics that are represented in our climate models. So early climate models had, about the amount of physics that would be useful if the Earth was a single point. They didn't give us a lot of information about regional climate change. They didn't have any horizontal heat transport, and they didn't really have any clouds, which is something we know now makes a big difference in climate change. So you can compare early climate models to the video games we were playing in the 80s. Maybe some of you are familiar with Space Invaders, but nowadays our climate models are more like playing a video game that's a lot more advanced. So our computing power has changed, and with that computing power, we've gotten much fancier technology in general, but our climate models similarly have made huge progress because now we can run many, many model simulations on multiple processors and get way more data out of them. So here's a little movie showing a cloud resolving climate model. And you can see that, while this video might not look perfectly like a satellite image, we can really resolve just using these equations describing the physics of the climate system to look at things like cloud cover changes regionally all over the globe. So it's pretty amazing where we've been and how far we've come. We test the accuracy of climate models by seeing how well they simulate the 20th century. We have weather station observations and satellite data spanning the 20th century. And so essentially we run the climate model over that same time period and compare it to observations to check that it's working well. Each one of these figures here shows historical observations in black and a different climate model simulation from different US climate modeling groups, such as GISS. This is NASA's model. This is the National Center for Atmospheric Research's model. And you can see that in all cases, climate models do a very good job simulating the 20th century compared to observations. One of the things we use climate models for is detection and attribution. So detection of climate change is sort of like, what is happening? How is our weather changing over time? But a key thing we need models for is attribution, or figuring out why are things changing? Who's causing that change? And a key question in climate science that I get a lot is, how could humans really be solely responsible for global warming? What about factors like solar radiation or volcanic aerosols? Could it really be our puny species dramatically altering the planet? And we know the relative impacts of natural and human-driven changes in Earth's energy budget, and we can actually separate them out. So for example, we know the amount of extra energy retained by the atmosphere due to greenhouse gases, due to changes in how the sun's energy varies over time, due to aerosols for urban pollution. And we can take a climate model, just like a video game, and run it with one of these forcings at a time and see what happens. Now, if we run a climate model through the 20th century and we just give it natural things, no humans involved, just volcanoes, just solar variability, we get this blue line. And you can see that right around 1950, this blue line diverges from what really happened here in black. So climate models cannot simulate what happened in the 20th century with natural things alone. If we add in human influence from greenhouse gases, climate models almost perfectly hit the target of what happened in reality. So this is one of the major ways we use climate modeling in my field, is to attribute climate change to human causes. How do we predict climate change? A key way that we understand what might happen over the next 100 years is that we use representative concentration pathways, which really just mimic how will humans respond geopolitically to the next 100 years of climate change. We have lots of options. We have the option to do no mitigation or a business as usual increase in carbon over time, or we can really get our act together and do serious or insane mitigation to pull down human emissions of greenhouse gases. So these representative concentration pathways describe plausible emissions trajectories that are based on economic and technology assumptions. So we run climate models into the future using those scenarios. And when we do that, we get some very consistent predictions from, tens of different climate models about what will happen in the 21st century. The first thing that is well known is that temperatures are likely to increase. This video shows the RCP 8.5, which is the business as usual, no mitigation scenario, and the temperature anomalies over time. You can see a few key features, such as the Arctic Circle warming much faster than other places around the globe. And you can see that as we spool through this video, towards the end of the 21st century, things are really getting weird and much hotter. We know that temperature extremes like heat waves are likely to increase in a warmer climate. Here in Texas, we expect that there might be between 1 and 3 more months of days over 100 degrees Fahrenheit in Texas, depending on where you live. So let me just say that again. 1 to 3 additional months of days over 100 degrees per these climate scenarios. The next thing we know is that, as I'm sure my co-panelists will talk about today, the number of water-related billion-dollar events and their costs has been going up over time. And here in Houston, we're no stranger to these major hurricanes that have been coming through. This is a basic prediction from thermodynamics. A warmer atmosphere can store more water vapor. So climate models show that the top 1% of precipitation events are likely to increase dramatically in a warmer climate. And I can tell you from personal experience that I was hooked to my co-panelist Eric's Space City weather blog multiple times hurricane season. Here's Hurricane Delta barreling through the Gulf. And there's multiple papers published over the last several years showing that the power dissipation index, the frequency and severity of hurricanes, these statistics are likely to change over time. So the frequency of both floods and droughts is likely to change in a climate scenario. We also know that areas like the Southwest US are drying and that they've been much drier in the past. So we're in for changes in temperatures, in the amount of water we have available, and this will stress our societies dramatically. And then finally, we know that Arctic sea ice and land ice all over the planet is decreasing. I'm sure you've seen lots of articles about this. All over the planet, we project that there will be loss of ice mass. And as a result of that, sea level rise. So our sea level rise projections from climate models show between 0.4 and a meter of sea level rise by 2100, but that does not account for melt of Greenland, which could be up to 6 meters if it were to collapse. So I'm going to leave you with a very key thought, which I hope if you take away nothing from my talk, please remember, when it comes to climate change, the science is simple, the impacts are serious, and the problem is quite solvable. So one of the things I've been telling my students these past couple of years is we really need to start focusing our conversations towards solutions, training our students and encouraging our peers to find solutions, and to demand solutions-oriented dialogue from our elected leaders, because the time to discuss this science and how controversial it is well gone. We need to start focusing on how to fix the problem. And then finally, on a lighter note, if any of you have K through 12 students, or if any of you are students in the room, there's lots of build your own climate model tools out there. So I'll post those in the chat so you can play with them on your own time, but there's lots of great resources online for learning more about climate models. So thank you very much. And I'm happy to discuss more about my research or any of these questions later in the panel.
Great, thank you very much. I'm not K-12, but I'll still be looking at the build your own models afterwards for sure. And I see there are some questions coming in already, which is great. And as I said, we'll leave those for the end for our roundtable part of the event. But for now, I'm just going to jump straight into our second panelist, our second speaker, John Nielsen-Gammon, who's a Regents Professor at A&M in the Department of Atmospheric Sciences. John is both a meteorologist and a climatologist, and I think at some point we'll probably be getting into the difference between those two things, and specializes in extreme weather events. He's the official Texas state climatologist and keeps our state make the best and helps our state make the best policy decisions possible based on data. John will be talking about how climate change leads to extreme weather events and perhaps a little bit of how that impacts Texas. So John, please go ahead.
Okay, thank you. And thanks for the invitation, and thanks for the drink. So Sylvia gave a great introduction to climate models, but there's one thing she said I'm going to push back on. She said the science is simple. My science is really hard. I'm proud of what I do. It's not that simple. But I think what she's trying to say is the basic science about how it is that we're warming the earth and how much. That part is actually simple. When scientists get together and argue over scientific issues in the climate realm, they're not arguing about whether we're causing climate change. That part's been established for decades. We're arguing about subtleties. Like actually, a very important paper came out 3 days ago on that seems to have settled the question of whether temperatures over the past 6,000 years went up by ½ degree globally or went down by ½ degree globally. That's the sort and I consider that a very important paper. But that's the sort of fine details that we're arguing over. I want to talk to you about extreme weather and how scientists figure out whether extreme weather is being affected by climate change. And I'm going to base this on a very good report that the National Academy of Sciences came out with a few years ago. And the way they framed it is that there's basically 3 ways that we can know or try to figure out whether extreme weather has been affected by climate change. And I'll walk through each of those 3 ways of knowing using 3 examples of extreme weather, which will be heat waves, heavy rainfall, and tornadoes. So first way of knowing is physical understanding. You know, the climate system is not a black box. As Sylvia showed, it's governed by equations that have been known for literally hundreds of years in many cases. And so we have a pretty good understanding of how at least the straightforward stuff ought to work. For heat waves, it seems indeed pretty straightforward that if average temperatures go up, the chances of having very high temperatures will go up also. And that's indeed what we see. The main driver of increasing heat waves seems to be not that the weather's getting more erratic in some sense, it's that the average is shifting, and so the extremes are shifting in the same way. With rainfall, we have a partial physical understanding. We know that, again, from scientific laws that have been known for centuries, the warmer the air gets, the greater amount of water it can hold in vapor form. So when it reaches capacity and there's still upward motion going on, that's when you produce rain. So if the capacity is greater, the amount of rain you can get in a given situation is greater. So there's physical understanding about how extreme rainfall will increase. With tornadoes, there's not a straightforward link with temperature. There's not a straightforward link with rainfall. We have a decent sense of what sort of conditions are favorable for tornadoes, but we don't have a basic expectation of how those conditions should change with global warming. So our level of physical understanding is different for those 3 cases. Second way of knowing is climate models, which you've just heard about. If a climate model is simulating climate change by having increased greenhouse gases in it and so forth, it's doing all sorts of stuff that satisfies the equations it's solving, and it spits out a lot of information. One of them could be, and is, that as temperatures go up, the extreme high temperatures go up also. That's produced by climate models. The fact that it's in the models and consistent with our physical understanding gives us more confidence that that's really something that we should expect to see. In terms of rainfall, climate models also show a general increase of extreme precipitation, but it doesn't happen everywhere in the models. And the reason it doesn't happen everywhere is that it's not just the amount of water that matters, it's also the type of storms that matter. And different storms can change in different ways that aren't necessarily straightforward. We're still, to some extent, trying to hash out how hurricanes are going to change. Some aspects of that we know pretty well. But as far as, say, winter storm tracks or the frequency of squall lines, that's a bit harder to pin down. So the confidence of extreme rainfall increasing in a particular place is not as high as the confidence of extreme temperatures going up. And with tornadoes, those are happening, typical tornadoes only, less than a mile wide. Sylvia said the climate models are simulating every point in the atmosphere. Well, actually, they can't. We don't have the computers to do every single point. They're basically doing points that are spaced about 25 to 50 kilometers apart. And so it can't simulate a tornado directly. I suppose that's a good thing. We'd be in serious trouble if we were getting 100-kilometer wide tornadoes marching through the central United States. So models don't tell us much about tornadoes. Again, higher confidence with the temperatures, lower confidence with tornadoes. The last thing is the historical record. It's fine if we expect something to happen, and it's fine if computer models simulate it happening, but it's also useful to know whether it's actually happening. And we've had, a degree Celsius of global warming already, so we ought to be able to detect some trends. And indeed, we can tell that frequency of extreme heat in Texas has more than doubled over the past 50 years or so. We can see it's increasing across the globe. So all the ducks are in a row for extreme heat. It's going up. We expect it to go up. Computer models show it going up. For extreme rainfall, we see the frequency of extreme rainfall increasing. Some work I've done recently for the Southeast United States says the odds of any given extreme rainfall event have increased throughout the Southeast United States, as long as you average over an area larger than an individual hurricane to get good statistics. Tornadoes, we've got records of tornadoes going back to 1950, but the problem with that is they're not very good for climate studies. People weren't going out and looking for tornadoes in the 1950s. There wasn't storm chasing back then. We didn't have Doppler radars that could say whether there's a storm spinning up that people could go on the lookout and watch for tornadoes. So we can't tell from the historical record whether tornadoes are becoming more frequent. So all aspects of extreme weather fit somewhere along that line between very confident for extreme heat, extremely unconfident for tornadoes, we don't even know the direction of change, and extreme rainfall, which should increase in general, but not necessarily everywhere. So that's the sort of how we do extreme event attribution and try to relate it to climate change.
Okay, thank you very much. I think we have a lot to go through on some of the concepts that you've talked about, and we'll have a few questions to go over at the Q&A bit. But before we go into that, I think I'll go ahead and introduce our third and final speaker, Eric Berger, who is a certified meteorologist, a former writer for the Houston Chronicle and current writer for Ars Technica, and the editor of Space City Weather, which I think, if Houston-based people in this event aren't familiar with Eric's name, they'll certainly at least be familiar with the Space City Weather page. As Sylvia mentioned earlier, when I was living in Houston, I was certainly glued to it all the time, particularly when we had extreme weather events approaching. And always refer to it for weather advice in Houston. And I think Eric Berger will be talking about specifically, going from the broad to the local, as we mentioned, some weather events in Houston. And I think, I'll go ahead and let you go through your talk.
Yeah, so we've done global models, we've done Texas with NG, and now we're going to talk about Houston specific for a few minutes. So that's right, I'm a meteorologist, I'm not a climate scientist. So I deal mostly with weather on a daily basis and not climate change. So I'll just talk for a few minutes and then leave plenty of time for questions. However, with that said, you know, when you watch the weather closely, as I have for 20 years in Houston now, you start to see changes. And those changes are increasingly backed up by data. One big change, which is unfortunate if you live in Houston, is that summers are getting longer. The first day of summer, if we define it as the 75th percentile day, which basically means that the warmest 25% of the year, you know, a couple decades ago. Basically, we're going to define it as the average temperature reaches 81.5 degrees. So that's basically nighttime temperature in the low 70s, daytime in the low 90s. And if we look at historical data, we can see how this is changing. So if we consider summer, this period of, you know, a few months, back during 1970, 1980, that period, which really was not all that long ago. The first day of summer typically occurred around June 13th and lasted until around September 18th. So that was just a little bit more than 3 months, which is not that bad. Now, if we look at the most recent 2-decade period, which just ended in 2020, so from 2001 to 2020, the first day of summer occurred 9 days earlier. The last day of summer was 9 days later. So now we're up to nearly 4 months of summer, basically almost all of June, July, August, and September. Then if you peek ahead at what climate models suggest about this, and I'm not going to go to the end of the century, I'm going to go to the middle of the century, which I hope to live to see. Summer is going to extend from not June to September, but actually late May through early October. So, you know, if you live in Houston, that's not exactly happy news to think about. You know, one of the big drivers of this really has been nighttime temperatures. The nights in Houston are getting warmer, and that's for a number of reasons. But we can again look at that and see how that's changing. So let's consider 80 degrees as kind of like the demarcation point between like a really warm night and a not quite as warm night. If it's 80 degrees or warmer at 11 o'clock or midnight or 3 a.m. when you walk outside, you know, you're still getting hit by a wall of heat and humidity in the middle of the night. Looking back at that period from 1971 to 1990 again, it was really rare to see a summer night that did not fall below 80 degrees. So maybe you would get one 80-degree night a year, maybe none. It was really quite rare. From 2001 again to 2020, the average ticked up a little bit to 3 nights a year. If we look back at this past summer, which, you know, if you think about it, in Houston, it was not like an extreme summer in terms of, you don't remember these really long heat waves, things like that. Fact of the matter is we had 20 nights where the temperature did not fall below 80 degrees in Houston. So by that measure, it really was an extreme summer. And so this has changed, you know, I look at weather, but this is climate change you can see happening in real time over the lifetime of my career. Now, some of this is probably attributable to increased development in the urban heat island effect, but you can see similar trends at more rural temperature stations across the region. And so the Gulf of Mexico is warming up. As it does so, our region is seeing less efficient cooling during the overnight hours. There's other factors, including a lower boundary layer, things like that. But you know, it's there. It's at nights in the summer. By the way, according to the global model or the climate models, we can expect 20 to 30 of these nights a year by the middle of the century, and obviously going up if we don't do anything about climate change. Finally, just moving beyond temperature a little bit. Talked a little bit earlier about precipitation. Obviously, Houston has had this string of nasty storms of late, including Hurricane Harvey, Tropical Storm Imelda followed right after. And the amazing thing about Imelda is that for the Beaumont area, which saw an extreme amount of rainfall during Harvey, Imelda was very nearly as bad. and it came right after it. And these were two historic storms right on top of one another. And then, of course, last summer we had Tropical Storm Beta, was a pretty strong rainfall event for southern parts of the Houston area. The current thinking on precipitation and hurricanes is that it's likely that the warmer climate increased precipitation by about 15% from Harvey. So the rains were worse due to climate change, but other factors really exacerbated the problem too, including particularly urbanization. When you build over all the areas that the water has to run off to, the water has nowhere to run to, and so it backs up. And so when we're thinking about actions to deal with climate change, which obviously is a very serious problem, we probably ought to think about land use as well, particularly in Houston, to mitigate the effects of that in our backyards. Because even without climate change, given all the development, Harvey and Melba and Beta would have caused very serious flooding problems. So I think I'll leave it there, and we can move into the Q&A period.
Fantastic. Thank you so much. Yeah, the idea of a May to October summer in Houston is definitely a little bit scary, and the 20 to 30 nights above 80 degrees is yeah, something that sounds a little bit scary. But yeah, let's move on to the Q&A part of the discussion. And I kind of wanted to start a little bit broad before we start going into some of the more specific questions that we've got before the event and that we're getting now. But we've talked about, our event is called Climate to Weather, and we've talked about climatology and we've talked about meteorology. We've kind of started with climatology with Sylvia, then John, who kind of hits both of them, and then meteorology with Eric. So I think by your presentations, we have a kind of an idea of what the differences between them, but how exactly are those different? And more than that, I guess, how, as sciences, how do they interact? Is there a lot of conversations between the meteorology and the climatology fields? Is there any rivalry? Why are these two separate sciences and not two different aspects of one science? It would be great if you could talk a little bit about that. And no one's kind of jumping in. So I guess I'll start by asking John, since you kind of like cross between both.
Sure, yeah, I started out in meteorology. I gradually got into climatology. The simple description is that the climate is the statistics of the weather. If you have one event, it's weather. If you have one event per year, it's climate. So they're not inherently different, but of course you're dealing with things looking at things happening on different time scales and often different, geographical scales as well. There's, just as much collaboration between meteorology and climatology as there is between other branches of atmospheric sciences. Like you got atmospheric chemistry, you got radiation transfer, you've got dynamics, you've got data assimilation and computer weather forecasting. So in the atmospheric side, climate science is just another branch of that. But climate science is so much more than just an atmospheric part, because the climate system, which you got a glimpse of in Sylvia's presentation, covers the oceans, it covers the land surface, it includes the ice sheets and snow, it includes the soils, and even continents colliding affects our climate in dramatic ways on millions of year timescales. So the distinction I'd make scientifically between climate and weather is a specialization in meteorology, but climate is really an interdisciplinary science that covers all sorts of different aspects of the Earth system and the people and life that lives on it.
I would say too that one of the most important aspects of what I do is not so much science, but communication. On a day-to-day basis, I'm looking at scientific information and understanding that, but then distilling that and sharing that in a way that that a broader public can comprehend. And so as part of that, I see, informing people about the weather and climate change kind of as both being important. But climate scientists generally communicate from scientist to scientist, whereas meteorologists communicate among themselves, but then talk to the general public much more frequently, and I think much more, or to some extent more comfortably, just because we do it a lot more.
Great. Well, thank you very much for that. I think that definitely clarified it for me. And I guess then starting from the climatology, I think I'll go ahead and ask, direct a question at Sylvia. In terms of climate models, you're predicting sort of large scale events across a pretty large deal of time. So how long do you have to wait in order to be able to get data to generate these models? And how, I guess my question is in terms of timeframes. How do you test and refine your models in terms of an actual reasonable time frame? How does that work?
So actually, a lot of the work I do, I showed in my talk that we constrain the behavior of climate models by validating them against 20th century data, but we also use periods of time in Earth's past, like the last 1,000 years or the last 10,000 years, or millions of years ago when the climate system was fundamentally different, to try to check that the physics in our climate models are working correctly, because the climate system varies on very long time scales. And so in order to properly check that our physics and our sort of understanding and our parameterizations are correct, we actually do go across many millions of years longer timescales to try to basically break the model. It's like, okay, well, is the model getting this very large temperature change in Africa that we observed in paleoclimate data from lake systems 6,000 years ago? And if it's not quite hitting those targets, then we have sort of these really interesting questions we can answer. Well, is it something we're not understanding well about vegetation feedbacks or clouds? And then I don't know if this is part of your question, but I guess in terms of time scale, another thing that I think is interesting to point out about getting data, we actually, we have observations from the 20th century. More recently, past several decades, we have really rich data from satellites. But then really beyond that, the only information we have to constrain climate system behavior comes from things like ice cores and corals and tree ring reconstructions of how climate varied back in time. So I don't know if that answers your question.
No, it definitely does. And I'll go back to John and Eric shortly, but I think I kind of just wanted to jump on that because I was interested in the graph that you showed with how different levels of mitigation strategies can change our projections of what these models are going to look like in the future. And you saw very dramatic changes in sort of what looks like a fairly short period of time. So I guess my question is not just how the different levels of mitigation differ between them, but how do you model them?
How do we model the mitigation scenarios themselves?
Yes, like what kind of data do you feed into the model based on what your mitigation sort of forecast is?
Yeah, so most of those are determined by the amount of greenhouse gas emissions. So all those scenarios, the biggest variable that matters as far as how hot does it get in the future is the petagrams of carbon that we put into the atmosphere. It's really, there are other variables that change. For example, like as I mentioned, the way that we develop these models is based on sort of socioeconomic indicators and activity. But sort of the biggest determinant and the biggest sort of boundary condition that we change over time are those greenhouse gas emissions. And then we let all of the other parameters in the climate system adjust to those forcings. Mm-hmm.
And going from that, and I guess sort of maybe directing this more towards John in terms of sort of we understand how these climate models, or more of how these climate models are built, but in terms of the mechanism to use these models and actually use them to change state policy or state laws and protocols? What is the mechanism for that? And one of the things that come to mind is, for example, in Houston, we talk a lot about floodplains, for example. How do you build from climate models into policy changes?
Yeah, it's probably a fair statement to say that nobody actually cares about whether the Earth's temperature is a couple degrees warmer. We don't live on the Earth, we live in particular places, and we care about what the consequences of that might be. So the climate models can simulate the consequences for weather around the globe, for things like simulate the consequences for runoff. Now we have components of climate models that simulate how vegetation changes, and so forth. So that gives us some big picture indications of what could be happening. Then to figure out what's happening at the local scale, there's a whole process that's called downscaling. Yeah, we made up that term, downscaling, that says, okay, if this is what's happening on a large scale, what does that mean about what should be happening on a local scale? How should the temperature in Houston change? How should the city core change compared to the suburbs? That sort of thing. And if you got local information, then you can look at all sorts of different consequences. Like, okay, does that mean that the folks that are growing rice down toward the southwest are not going to be viable because the amount of water is going to be less, or because the climate's going to be too hot or too variable, or what have you. So there's a whole branch of climate science that's looking at the impacts. In fact, you hear about the IPCC reports that come out every few years. The next round is due out in a year or two. The first one is all about the physical science, what's going on with the climate system, which is the stuff I work on, which is the stuff Sylvia works on. The second part, second volume, many chapters, is the impacts. What's that mean for agriculture? What's that mean for energy? What's that mean for water supply? What's that mean for diseases? All of those consequences, because those are the things that the people care about, things that industry cares about, what have you. So that's the part that get people's attention. That's the part that get policymakers' attention. But it's fine to have their attention. What do you do about it? And that's the third volume of the IPCC's reports, which is, what are the policy options? And it's fine to say we've got a big problem with climate, we need to do something about it. But then the next question is, well, what can we do that'd be effective, that'd be cost effective? And it's at that point that I say, sorry, I'm a climate scientist. You can talk to the engineers and the economists and all those folks that actually can solve the problem. I can just tell you got one.
All right. I guess I'll move into the local then, since we were kind of doing that direction, and towards Eric. As I said, living in Houston, I think like a lot of other people, we're constantly glued onto Space City weather, and the very exact predictions that you often make in terms of meteorologist, and you just made some pretty sort of clear predictions of what might happen in the future. But I think we remember from back when we were children, weather forecasting being pretty bad. It clearly seems like it's gotten a lot better in recent years. So could you talk a little bit about why that is, and how it, I'm assuming, also relates to some of the work that scientists like Sylvia and John are doing?
So Sylvia showed Space Invaders, the Space Invaders computer game, as part of her presentation, and then compared that to the resolution of a modern video game. And the fact of the matter is that the primary driver in our understanding of climate, or understanding of forecasting, has been increasing computing power, which has allowed us to run not climate models, but weather models, which don't look at averages of conditions over 50 or 100 years, but look at weather conditions over the next 16 days, basically, the global models do. And as computing power has gotten much better, the ability to sort of shrink that box of point data from 20 kilometers across to 10 kilometers across to 5 kilometers across has allowed us to get much better resolution, much better output in terms of modeling. Now, there's been a lot of other factors that have gone into it. More sophisticated modeling, much better initial data that we've been able to feed into the models. But the fact of the matter is that a 3-day forecast in like 1980 is now about as accurate as a 7-day forecast today. So, or like the average error for a hurricane track today at 5 days is about the same as it was at 2 days out, several decades ago. And so we've seen this dramatic sort of shrinking in the area. And, probably the most powerful example of that I can think of, that people may remember is back in 2005, we had a major hurricane, Rita, out in the Gulf of Mexico. Incredibly threatening storm, 175 mile per hour winds. And at 3 days before landfall, the track for that storm, the cone from the National Hurricane Center, almost covered the entire Texas coastline. And so, and the best track sort of brought it very near Houston. So it was quite a terrifying storm. 15 years later, we have Hurricane Laura, which, is not exactly on the same track, but it's another major hurricane in the Gulf of Mexico. And the cone of that storm was such that 3 days out, Houston was just outside of it, right? And so 15 years ago, we had Rita, we had this enormous evacuation. Dozens of people were killed on the freeways trying to get out of town. It took 20 hours to get from Houston to Austin, 24 to Dallas. And it was an absolute nightmare for anyone who was here and lived through that. This past summer, thanks to much better hurricane modeling, we narrowly avoided a similar evacuation scenario because Houston was on the edge or outside of the cone. And we knew enough, the cone was much smaller, and we knew enough to basically say, probably going to miss, right? So, let's not evacuate. And so that just makes an enormous difference in people's lives.
Yeah, no, I definitely remember some of those conversations happening around Harvey as well, whether or not to evacuate at the time. That was something that was heavily discussed on the days coming up to Harvey. And I think it was based on some of what happened with Rita. In terms of extreme weather, I guess one of the questions that we've got already from one of our participants is on the impact or shifts in larger scale climate processes like El Nino and La Nina. Do we expect these to shift dramatically? And I guess maybe for a lot of our audience, specifically, do we expect them to affect Houston in any way? So I don't know who wants to go for this. John, maybe. Oh, Sylvia.
I think we could probably all tag team this question, but I'm very biased, and I think this is an awesome question because I actually do a lot of research on how climate change will interact with modes of natural variability like El Nino and La Nina events. And to answer your question, the jury is really still out. I mean, there's hundreds of climate scientists working on this exact problem of how will, warming in the tropical Pacific alter these, really loud modes of natural variability. So one of the things my grad student is working on is if we warm up the tropical Pacific, how does that change rainfall patterns associated with El Nino events? And it's very difficult to see what happened in warmer time periods in the past to the El Nino Southern Oscillation, for example. So I guess I'll just tell that question asker that you've hit the nail on the head in terms of things we don't properly understand yet.
And there are two different things we don't understand. One is, El Nino itself might become more intense or more frequent or the opposite. Both of those are sort of possibilities. And then the other part is even an El Nino of the same intensity that would affect the weather differently potentially, because, for example, it affects Texas weather mainly by altering the position of the jet stream. And so it's mainly during the cooler time of the year when we get jet stream weather that El Nino affects things. Well, if the jet stream shifts position because of climate change, that's going to, you know, in some sense affect the impact of El Nino locally, but also might affect it globally if it's in a place where the jet stream no longer interacts as strongly with what's happening in the tropical Pacific. So those are the sorts of issues that come up that you know, folks like Sylvia and her students are trying to deal with.
I don't know, Eric, if you wanted to add anything to this or not.
No, that's the kind of question I would ask John or Sylvia as a reporter or meteorologist, because I don't know.
Before we move away from this question, I think maybe it would be good to also define a little bit of what we mean by El Nino and El Nina, because I just realized we jumped straight into the actual sort of crux of the question, but some people might not actually be familiar of what these systems are. So if any of you could jump in on that, I think that would be great. Sylvia, maybe?
Sure. I was going to see if John wanted to take that, but yeah, so.
Berger to speak up since he's the communicator.
El Nino was Chris Farley on Saturday Night Live. That's
yeah, El Nino. Wow, that's such a good bit. So I guess simple answer is there are things that the climate system has that happen to it. You know, there are things that happen to the climate system, like how much greenhouse gas is emitted, and then there are things that the climate system does all on its own. So there are what we call modes of variability that oscillate back and forth, you know, on timescales of maybe 2 to 10 years, depending on what that pattern is. And we can see, yes, we can see these patterns sort of, you know, seesawing back and forth over time. And you know, for example, El Nino and La Nina in particular are just this warm mass of water sloshing back and forth in the tropical Pacific. And because the tropical Pacific is basically the heat engine for the entire planet, thank you, John, that locus of warm water actually affects weather and rainfall all over the globe. So that big hot water mass is moving sort of the convective cell over the Pacific Ocean such that weather propagates outward. This is just great. I feel like Vanna White. And so it actually has a major impact on the rainfall we experience in the US. And, you know, for Southern Californians, for example, they tend to get really heavy rainfall during El Nino events and really dry conditions during La Nina. Wow, just incredible. So yeah, that's what ENSO, we call it ENSO, the El Nino Southern Oscillation. That's what it is. It's arguably the loudest, most noticeable natural pattern of climate variability on Earth.
That was an incredible combination of efforts to answer the question. Thank you very much. I really appreciated the illustrations. That was great. Thank you so much, Sylvia and John. And I guess, I mean, this was such a collaborative answer to this question that I might just go back to that factor and kind of like how these different aspects of climate science work together. Because there was someone who specifically asked how mistakes and successes, and I guess, you know, as we go in weather models like from Eric, feedback into the work that then Sylvia and John do on the broader level.
I think from a public communication standpoint, probably the biggest challenge, or one of the biggest challenges that climate scientists have to deal with respect to meteorology, is the idea that, I mean, as a meteorologist, I will freely admit that, you know, in a forecast out to about 5 days, highly confident, generally. From 5 to 10 days, you can generally say something intelligent about the weather. But you know, when we get to a forecast of 10 days or beyond, in most cases, not all of them, but most cases, I just kind of throw my hands up in the air and say, you know, who knows? I mean, is it going to rain for this person's wedding, or is it going to be hot, or is it cold? Oftentimes the answer is We just don't know. And so then the natural question that climate scientists have to deal with, hearing that from meteorologists on a day-to-day basis, is, well, if you don't know what the weather's going to be like in 10 days, how do you know what the climate's going to be like in 50 years? And so I think that's one sort of challenge.
I saw Sylvia nodding, so I thought you were going to add to that, but we can. I mean, that's a great point, and I think communication is probably something that we'll come back to. But in terms of the modeling, and both, I think this question is probably directed to everyone in terms of both, you know, weather forecasting and climate models. Are we at a point right now where we're limited by computational power or by data inputs?
Have we ever been in a place where we haven't been limited by computational power?
Yeah.
I mean, the one of the primary reasons for developing computers, the immediate application in the 1950s, was weather forecasting, and weather and climate have always been the biggest customer for one of the biggest customers for advanced supercomputers ever since. You know, if we had a computer that was 1,000,000 times more powerful, we would still not be satisfied, but it would be a tremendous advance over what we do right now, because we have to basically, we can simulate the stuff that's on a large enough scale we can simulate directly, but everything else we just sort of have to estimate statistically through parameterizations. And you know, it'd be great if we got to the point where our climate models actually simulated tornadoes, and I could give you an answer to that question that I posed at the beginning.
Yeah,
Sylvia,
so I'll completely agree with. I'll completely agree with that. I mean, if you want to run a climate model ensemble such that you have, you know, multiple versions of reality for 100 years, those simulations take 6 months to run on multiple supercomputers. So it's incredibly computationally expensive to run climate models at high resolution. And then, yeah, I guess the sort of interactions between numerical weather forecasting models and climate models, I do think that, you know, there are lots of people in our respective fields that run both types of models. And I have colleagues who exclusively only run weather forecasting models. And then, you know, my atmospheric science colleagues, we look at, you know, water vapor in the atmosphere, and we do actually talk and exchange ideas and try to help each other. Oh, you know, we just figured out this bug in our atmospheric, you know, convection code, and maybe we should, you know, translate this into the model physics. So I do think, Pedro, that the two communities do talk a lot, and there are lots of people who bridge the two sort of modeling communities in our field.
Yeah, that's definitely really, really great to hear. We have a few questions, both from before the event and that we're getting today, about sort of more kind of general forecasting. And one of the questions that we have is about the next ice age. Do we have any idea when a next ice age might kick off, since they seem to happen at regular time intervals?
Yeah, I can take that one, I guess. It seems that we have, you could regard this as a beneficial consequence of global warming. We seem to have missed our chance at the next at the ice age stopping at our current station and let's getting on and going down the road to ice-covered northern North America. Because temperatures are going to be elevated for probably several thousand years, the orbital configuration won't be right by the time the Earth cools back down again. We should have been near the end of the glacial cycle, but and in fact, the little ice age may have actually been what was supposed to be the start of the next ice age that we then managed to avoid by the Industrial Revolution. Given that, the next time the train is going to be approaching the station is probably 20,000 years from now. So we have managed to avoid that consequence.
20,000 years, okay. there were quite a few, or I guess I'll just jump into something else, since we've talked extensively about climate change and global warming, and you just mentioned the effects on a potential start of an ice age. We've talked about some of the mitigation strategies and the impact that they may have going forward on Sylvia's models. And I guess the question that a lot of people are asking is do we have enough time? Are we doomed to have some degree of irreversible effects from global warming, or is there still enough time to work on some of these mitigation strategies that will change the curve? And Sylvia, I see you just
yeah, so I think that I maintain a lot of hope by the all hands on deck approach being taken by the new administration. We will need to mitigate and adapt in every possible way. We've talked today a little bit about extreme changes in temperature, and these types of changes are likely to cause things like mass climate migration and potentially refugee crises. I think that we are going to see serious changes over the next 50 years. And I think that we have tremendous opportunity to innovate, and there's a lot of really exciting research going on right now with like carbon capture and storage technology and geoengineering. There's a lot. My attitude is that we will need to do all of these things to fix the problem. There's a really great book by Anaya Elizabeth Johnson called All We Can Save that has a huge glossary of all the things we'll need to do simultaneously to curb warming at 2 degrees Celsius, for example, which is what climate scientists consider safe levels of warming. But I think that it's always interesting when people say, oh, we only have a decade to fix the problem. That's like asking for a 10-year extension on a 50-year assignment overdue. So we need to start making these changes ASAP. But anyway, I hope that, I hope my hope can give other people hope.
It's definitely good to have some hope. So I appreciate that. And John, I know that you have something to contribute as well.
Yeah, I mean, I've had such good feedback with my computer graphics. I thought I'd give you another one here. I think this is how people often think about climate change. That either we're not screwed or we're screwed, and eventually if it gets warm enough, we're screwed. And there's a couple of problems with that conceptualization. So first of all, there's so many different aspects of climate change impacts that coral reefs get screwed fairly quickly, whereas boreal forests can do just fine for quite a long period of time. So there's a continuum of negative impacts and some positive impacts, mostly negative. So there's no discrete cutoff really for when the temperature rises too much or it's too late. We need to set targets, but every little bit that we do gets us farther down in this direction and makes some combination of aspects of the climate system less screwed than it would be. There is the potential for some things actually being tipping points where you actually do go from not screwed to screwed, but we don't know what temperatures those correspond to. So even there, it's basically you're increasing the odds of being in the screwed territory as temperatures get warmer, but there's not any specific cutoff that scientists can establish that say, yeah, there's the tipping point. We can't go over that number because bad things will definitely happen. It's all a continuum.
Thank you. That was, yeah, and thank you for the graphics as well. And actually on that point, we did have someone ask what the book was that you were showing us the graphics before from. So if you could just...
this is one of the book textbooks that I use for my physical climate class. It is suitable for a technically literate audience. It has calculus in it. It doesn't actually derive anything, but it's got the equations of motion that Sylvia put up. but it's very readable. It's by a very good scientist, yeah, I recommend it for a good basic physical understanding of the climate system and how we deal with it.
Great, thank you very much. We are approaching the end, but we still have a few questions in terms of specifically some of the data and some of the climate models that we've looked at. And one of the things that we were asked were, how do initial conditions matter in climate model equations? If the weather is chaotic in a mathematical sense, how do you establish the initial conditions? And do the models allow for errors on our estimation of them?
Yeah, so one of the major ways in which weather forecasting models and climate models differ is that climate is a boundary value problem and weather forecasting is an initial value problem. So in weather forecasting, which Eric can describe way better than I can, we start the model with a huge array of conditions from satellites and radiosondes, and we give it the exact state of the atmosphere and run it forward in time. And with climate modeling, we give the model a boundary condition. We say, okay, here's the greenhouse gas forcing. Here are major ways in which the planetary energy balance could be altered. And the initial conditions are just set to be either observed, state of affairs on the year we're starting the model run. We might initialize it with sort of an average if we're doing a run that might be something like what I do 20,000 years ago. We have information from ice cores and we give it sort of a mean state that we think is reasonable. But those initial conditions matter far less than the boundary conditions. And one of the things we do to generate these ensembles, or we want to see, I showed you those pictures of the 20th century simulations. You probably saw all those individual little wiggly lines. We run the model, 20 to 100 times over the same time period. And we just put a tiny little perturbation into the air pressure in the initial conditions to make those ensembles. Now, the question about uncertainty, I think those types of initial conditions uncertainties are much more impactful for weather forecasting because, in our climate model simulations, we essentially have, a lot of convergence in the simulations, again, depending on how much CO2 is in the atmosphere, or if there's a big volcanic eruption in a given year.
I do want to go into a few more questions on the models, but I want to make sure that we leave a little space in the end to talk about communication, because I think it's very important. We've kind of touched on it a little bit already. But before we go into that, I guess one of the questions the other question that we had in terms of model building is, I think you've mentioned some of this already, but do you only work with historical data, or do you test your models as new data comes in each year?
One additional year of data is not especially useful. What is useful is additional types of data that weren't available before. So one question I answered in the Q&A box was about ocean temperatures. And since about the year 2005, we've had observations of temperatures 2,000 meters down into the ocean, a global international effort to do that. Until we had that, we didn't really have any way of knowing whether the models were correctly simulating how much energy was being stored in excess by the climate system because of carbon dioxide and other stuff. And that's obviously a very fundamental thing that you want to know. Now that we have that, we can tell. Now that we've got satellites that are measuring solar intensity outside of the atmosphere, we can tell exactly how intense the sun is and how much it fluctuates without having to worry about what's going on in the atmosphere to attenuate things. So it's the new types of data that make a difference more than having an additional year of the same data.
And in terms of the types of data, there's been a few different questions about oceans and ocean temperatures. How do ocean temperatures work into your models, either weather or climate? And sort of related to that, based on some of the models that Sylvia showed, Are the currents faster in the Arctic Ocean or on the northern parts of oceans? And what do we know about how far down into the depths of the ocean the temperature is warming? So a lot of questions there, all kind of related to ocean temperatures. If you can talk a little bit about them, Sylvia.
Yeah, sure. So we model ocean temperatures just like we model atmospheric temperatures. So as I mentioned, the evolution of the state of climate, oceanic climate evolves in time. Sorry, there were three parts to your question.
Yes.
The ocean current speeds. So that's an interesting question. Actually, the dominant ocean circulation pattern in the North Atlantic is the thermal haline circulation. So we have the Gulf Stream carrying warm water up into the Arctic Ocean, where it then sinks down. And actually those currents, this data is very recent and it's a bit controversial, but people actually think those currents are slowing down. And that's caused by a lot of freshwater ice melt coming off of the Greenland continent, sort of interrupting the sinking of salty water around the Arctic Ocean. So I don't know of any studies that talk about currents accelerating. And then as the final answer to your question, we do have measurements of ocean heat content at different depths in the ocean. So we can measure sea surface temperature changes. And I have a figure I can try to find, but we do know that the ocean is heating at depth as well as at the surface. So that's actually much scarier because the heat capacity of the oceans is so much higher than the atmosphere. And so that heat that gets stored in the oceans is going to have a long time scale of attenuation.
Yeah. Thank you very much for that. And as we are starting to approach the end of the event, but as I mentioned, I did want to spend a little bit of time talking about communication, because I think both in terms of climate science and meteorology, that's really that's obviously really important for all of the reasons that we've talked about before. And I think I'd start with Eric. In terms of meteorology, I think one of the things that when people hear that there's X% of chance of clear skies, there's 80% of chance of clear skies, there's 70% of chance of rain, they often treat that as a certainty rather than just a prediction that is right 70 or 80% of the time. So how do you communicate these probabilities successfully to the public?
Well, that is one of the great challenges of being being a meteorologist and sort of communicating, like the percentage of rain. If you say there's going to be a 30% chance of rain, effectively what that means is that across the area for which you're forecasting, 30% of that area is likely to get rain. But if you're in an area that doesn't get rain or does get rain, it just, it's based on your expectations, completely messed up. And so what we try to do is not so much provide precise percentages, but sort of explain more about things that we have confidence in, things that we don't, right? So we're very confident that the temperature tomorrow will be, such and such, or we're very confident that this hurricane is not going to affect Houston. Conversely, with a storm like Laura, where there's a lot of uncertainty, we were very open about the uncertainty. And so it's more sort of where we found success, I think, is just being honest with people about what we don't know and being very explicit about that.
I think that probably applies to everything. I mean, that's certainly something that, all of us who work in the sciences need to definitely be cognizant of. I think when we talk to the people, to the general people about science, did you ever get, I'm assuming you do, sort of nasty emails from people who say, hey, you said it was going to be 80% clear skies and then it rained? Does that happen a lot?
It doesn't happen a lot. No, it's actually shocking to me the amount of positive feedback that we receive.
That's great.
I've worked at a newspaper for more than 15 years. And so I've seen that most of the feedback you get there is negative versus positive. But in this case, even if we bust a forecast, people are pretty understanding about the fact that that weather is kind of somewhat unpredictable. I guess we're just lucky. I mean, I think it comes back to being genuine with people about kind of what we know and what we don't, and being more right than wrong, I guess, over time.
That's that's really great to hear, and I think I'll use that to kind of move on to what's probably going to be our last question, but talking about communication and communication with the public in terms of global warming. And I think I'll start with Eric and then move on to John and Sylvia, because I'd love to hear everyone's views on this. But is there a specific way that you talk to people about global warming or about climate change, particularly the people who might be skeptical about it? And are there any good sources that you could share for people who might want to know more about it? And I'd love to hear what you all have to say about that. Maybe starting with you, Eric.
So I think with global warming, climate change, it's extremely difficult. It's become, it's been such a polarizing issue. My general sense from experience is don't try to beat people over the head with data, because it's just not going to work to a large segment of the audience. You really got to meet people where they are. I mean, there's a saying that weather is an extremely local phenomenon, right? People really only give a crap about the weather where they're going to be, right? Generally, they don't care about what it's going to be like in Dallas, or even if you're in downtown Houston, you don't care what it's going to be in Katy. And so, if you're going to talk about climate change, for a lot of people, you've got to sort of drive home locally what it means to them, and try to find ways to connect. And I think probably the most effective way, I've been able to do that is sort of through people, experiencing temperatures and things like that, again, over the last 15 or 20 years, because it has been noticeable in Houston. But it's an extremely difficult question. And, when it comes to communicating climate change, I'm afraid I don't have any answers.
Yeah. Well, I mean, I think for anyone who lives in Houston, telling them that in the long run, we'll start experiencing summers that go from May to October is definitely something that's going to call people's attention. I agree with that.
Yeah.
But I guess, John, do you have anything else to add in terms of that? And I saw that both you and Sylvia already put some resources on the chat, so thank you for that.
Yeah, sure. So yeah, if you hope to win an argument with a climate skeptic, you're probably out of luck. First off, they will be resistant to you changing their minds in general. And unless you know a whole lot about climate science than they do, and can convince them that actually you do know a whole lot than they do, then forget about it. So an alternate approach I like to take is treating climate science as though it's not political. In other words, not making a big deal of it, saying, okay, well, the long range forecast has right now has a 60% chance of significantly above normal temperatures for February through April. Part of that is because we've got a La Nina, and part of that's because of the long-term global warming trend. And if you treat it as something that is matter of fact, it's going to be hard for anybody to actually raise the objection, and it becomes just part of the established set of information that people have to work around and deal with.
Thank you. And Sylvia, anything else that you wanted to add to that?
Yeah, so I can tell you that I actually ask that exact same question to a lot of my mentors and peers who are excellent science communicators. I do a lot, I guess I do a lot of work with children and with K through 12 students. And I feel like, educating college students and, explaining over and over again, science is not a partisan issue. Science is not a partisan issue. Climate change is not a partisan issue. And, getting this information to K through 12 students is really, really important. With adults, I guess, who, I encounter who question my expertise, I usually try to find common ground and build consensus around the fact that, for example, we all want clean water, we all need clean air, we all want livable temperatures. Most people care about conservation of green spaces and, care about being able to visit national parks, and even, lots of people that I meet in Texas care about hunting or birding. And, these are sensitive systems that could go away very rapidly if we don't fix things. And so I try to listen and make it more personal and see what they care about, but it is tough. And I have a lot of experiences, monthly with people on either panels or even sometimes students who really question my authority. And probably part of that is because I'm a young woman, but it's tough. And I try to avoid sort of hammering them with credentials and facts like John mentioned and Eric mentioned, but once you're out of tools, it can be really hard. And I think, I also teach my students, we have a whole lab assignment about how to talk to a climate change skeptic, because there are about 10 or 15 very common arguments that you hear people say or use, like, oh, it's snowing, it can't possibly be climate change. So I try to train my students explicitly on how to identify and combat those arguments, and be ahead of the game. But yeah, I think it has become so emotional and so tribalism-y. And I think showing people up front that you care and then sort of slipping in, oh, I am actually an expert on this, is a good way. And on a final note, I put the Yale communication surveys in there. 75% of Americans know that climate change is happening and it's caused by humans. So that's good.
Yeah, no, I mean, that's definitely reassuring. And all we can do is to, follow your advice and continue talking about the science, but continue talking about the science in a empathetic way. And that's kind of what we try to do here and what we'll continue to do. I think at Taste of Science, and it's great to have experts like the three of you to be able to join us at our events and talk to people about the science behind these complex issues in an informal way. I think that really, really helps. And with that, I think we'll probably this is a great place to sort of close the discussion. And we'll continue to organize events like that. And I hope that you enjoyed the discussion, that everyone who was here. And if you did, please, follow Taste of Science, our mothership organization, and Taste of Science Houston on all of the different social networks, and go to tasteofscience.org, our website, to keep an eye out on future events. And as we said earlier, this is only the first event that we're doing today. There's going to be a second event later today, which is going to be our first ever Spanish language event. So if we could just bring Jenny Masi again to give us a quick reminder of what that event's going to be about.
So the event is called, as Pedro said, it's in Spanish, it's called 2020, 1 year to pandemics. And they're going to talk about the science behind the vaccines, and they're going to clarify all the myths around the vaccines and all the misinformation that is going around in social media. So now I'm going to repeat all this information in Spanish for those who speak Spanish. En media hora va a empezar un evento en español organizado por la Organización Nacional de Taste of Science, llamado 2020, un año y dos pandemias. Este evento va a discutir la ciencia detrás de del desarrollo de las vacunas hacia el COVID-19, y va también a tratar los puntos y clarificar todos los mitos alrededor de las vacunas y toda la desinformación al respecto. En caso de que no se puedan unir a este evento que empieza en media hora, el evento va a estar publicado en nuestro canal de YouTube. Muchas gracias.
Gracias. Thank you, Jenny. And with that, I think I'll go ahead and close the event. Before I do so, I really want to thank Sylvia, John, and Eric, all three of our speakers. I think that was a really, really great discussion, and I certainly learned a lot from it. So thank you so much for accepting our invitation and joining us for our event today. Thank you, obviously, to everyone at the Taste of Science Houston team who was managing the event in the background and making sure that we were going through as many questions as we possibly could. And obviously, thank you to everyone who joined us, and specifically everyone who sent us their questions. We tried to go through as many questions as we could. We received a lot of them. And if we didn't manage to get to your question today, we will definitely do our best to follow up with them on our Facebook page. So please, if you are not following us yet, make sure that you do, and we will get back to you as soon as we can. Feel free to email us if you have any further questions based on some of the stuff that we've discussed today. We are still in the middle of a global pandemic, so we will be continuing to organize some of these events virtually, which is does have the added bonus that you can join us from everywhere in the world. And I'm joining from Portugal, as I said in the beginning. So please go to our website, go to our social media pages to keep up with everything that we're doing, and join our events in the future. Hopefully we can go back to in-person events at some point soon, and hopefully we'll be able to host John, Eric, or Sylvia at some of those in-person events in restaurants and bars around Houston. But until then, please continue wearing a mask. Please continue social distancing and washing your hands, and hopefully we'll all be vaccinated on the other side of this soon. So thank you very much for joining. Thank you very much to all of our speakers, and we'll see you on our next event, whenever that is. Thank you.